I'm not really in the mood, but we'll do it anyways because you need to learn things and I got to provide instructional time. So, yesterday we talked about the idea, after training you on how to use a voltmeter that we don't get to use today, we talked about the electric potential energy and the electric potential. And one of the things that I want to point out is that if you have an idea about what the electric potential is in a region of space, you then have an idea of what the energy will be like for particles in that region of space. I tried to make it kind of akin to, what's the word I want to use? Topography. Do you guys know what a topographical map looks like? Who in here doesn't know what a topographical map looks like? Okay, so if you know, then you understand that a topographical map will have a whole bunch of, they're not circles, but they're like, what do you think about these equipotentials? Would they be evenly spaced? Is a change from here to here, a distance d, going to produce the same change in potential as a change from here to here? Would they be the same change in potential? Now think about it for a moment. The change in potential is equal to minus E dot, in this case, I'd say dr, as we travel along a radial. Is that okay with you guys? The electric field here isn't uniform. So the electric field here, which I'll say E1, to the electric field here, E2, is that as big a change as the electric field from 3 to the electric field at 4? Where is it a bigger change in the field? In this area A or this area B? B is a bigger change in the field, so I think I'm going to have a bigger change in energy if I travel along B as opposed to A. So I don't think my equipotentials are going to be uniformly spaced. I think as I get closer to this charged particle, they're going to get very closely spaced as the electric field gets bigger and bigger and bigger, right? We know the electric field shape mathematically. As R gets small, E gets big really fast. And then as R gets big, the change in E gets smaller. So I would argue that it's probably much harder to go from E3 to E4 than it is to go from E1 to E2. You guys all okay so far? We following along okay? So I don't think I would have evenly spaced equipotential lines here. I think if I wanted to divvy it up in 1 volt segments, boy, the lines are going to be way close together, close to the particle, and way farther spaced away from the particle. But we don't have to guess. We could figure it out. We could figure out what an expression would look like for the electric potential near a point charge. We have everything we need to figure that out right here. So let's figure it out. Let's find the change in potential going from location here to location here. Okay? I'm going to do the math on it. Now, to do this math, I'm going to need some placeholders. And you'll forgive me, but those placeholders, I want to make a different color. So let's say this is R1 and R2. And we're going to go here to here. All right? Everything okay so far? Any questions? So I want to find the electric potential difference, and we're going to go from 1 to 2. This will give us the change in potential. There's not much to do here, but I will have to evaluate all the things we've talked about in the past. Dot products, direction of vectors, stuff like that. Our electric field is not constant from R1 to R2. So we're going to have to integrate the expression for the electric field from R1 to R2. So the first thing I'm going to do is drop in the expression. But before I do that, let's just take a minute and evaluate the dot product because this expression doesn't have the direction in it. So can we agree that the electric field points in the direction of R? So the direction between the electric field and a small change in R is going to be 0 degrees. I'm just saying that if I look at this place right here, the electric field is radial, so it's got to be in that direction right here. And dr points in the direction of the radius, so it has to be in that direction too. So when I go to evaluate the cosine, I'm going to use 0 degrees for my dot product. Is that good? Does that make more sense now? Okay. So when I come back over here, my next step was to consider that, so I've now considered it. I drop the vector parts, drop the dot product, and put my little cosine 0 degrees over here just as a reminder that that's what I chose to do. Am I good to keep going? All right. I have to drop in my expression now for the electric field. So if I want to find an expression for the potential, I need to drop in my potential, my electric field. No, stumbling all over my words. So R1 here, R2 there, Q over 4 pi epsilon naught R squared dr. Remember this. Oh, I lost my negative sign. So put my negative sign back. Okay. Now this next thing is just an exercise in mathematics. It's not really physics, but we'll do this exercise here real quick. All right. I'm going to go ahead and take a look at everything that's in my expression. And I know I put a capital Q there, but I think I labeled my charge little q, so I should probably make a change so that's consistent. So let's do that too. I want to be consistent with my diagram. Now, as I go from R1 to R2, does the point charge change? No. As I go from R1 to R2, does 4 change? Does pi change? Does epsilon not change? Does R change? Okay, so anything that we just said doesn't change can come out of the integral. I know you guys are still going through calculus, many of you, so I'm taking the math part of this pretty slow. So pull out the Q, pull out the Q, the 4, the pi, and the epsilon naught. All right. Now, I do have to integrate this part, but you've learned the rule for this. And so if you don't remember the rule, this is a polynomial. So I can use the polynomial rules for this. Add 1 to the exponent and divide by the new exponent. To make this look more like a polynomial, it might be in your interest to remember that this is going to be the same as saying r to the negative 2 power. So for the sake of this antiderivative, I'm going to add 1 to that exponent. That's going to give me r to the negative 1. And I'm going to multiply by, I'm sorry, divide by the new exponent, which is negative 1. All right, so we've done all the calculus. All that's left is for us to put in our value for r and deal with any sign issues that we might have. So I'll have negative q, oh, I dropped the negative sign from earlier. I keep dropping this negative sign, sorry. got to go back. This negative sign I didn't write out front earlier. So I got to put it back in. So I've got negative q over 4 pi epsilon naught times negative 1 over r2 minus negative 1 over r1. That all okay? All right. Now, this is the change in potential going from R1 to R2. So I'm going to write this as a change in potential from V2, V1. Does that make sense? Because we're going from 1 to 2. So our initial place was 1, our final place is 2. I'm going to take this negative sign and distribute it, which makes all of these negative signs positive. And that gives me q over 4 pi epsilon naught r2 minus q over 4 pi epsilon naught r1. That's my change in potential. Now, I don't know for sure, without doing the math, that those original two places I had marked before are going to be different, but because it's the reciprocal, probably. All right. Yep.
I'm a little bit confused on the visual representation on R1, R2. If you could go back to the graph. So is R2 supposed to represent like it's the same angle as R1, just a little bit further, or what?
You mean because I didn't go straight along the same radial?
Yeah.
To explain this, I mean, I could say yes and make it easy, but what I really want to say is it actually doesn't matter. So, how about I explain why it doesn't matter? You guys okay for just a second? dr represents the direction we were kind of going, which was a bit at an angle, right? I drew it to be like aligned with E because they almost look like they're exactly aligned with E, right? I want you to imagine something though. What if instead I want to make this look right, so I don't want to use two arrows that are the same size. What if R1 and R2 were there, but they're the same distance away? But I'm going from R1 to R2 in this direction. Okay? Consider what we would be doing if we did that. The electric field would be in this direction here. But in this circumstance, dr would be this way. Right? What would that do to our dot product? Right. So what this tells me is that going from here to here offers no change in potential. It doesn't contribute to the change in potential. So it doesn't really matter what path we take to go from R1 to R2. In fact, what we say about this is that it's path independent. And consider it this way too. This motion going from R1 to R2, that's very particular. But if I look over here, even though it's a small change, and we look at dr was actually at a slight angle to go from R1 to R2, the component of r that was this way never mattered because I was always producing a cosine of 0. Only the component of r that was along the direction of the electric field mattered. So those off-axis components of r were never going to contribute anyways. So it doesn't really matter the path I take. I could take this path, and it'd be the same change in potential. And I'll remind you that ultimately the potential is about the place, not the charge. So regardless of the path taken to get there, the change in potential between the two locations It's just about the beginning point and the end point. And I'd also bring up something else here that's kind of minor, but I think it'll play a important role later. Remember how displacement didn't matter the path? That it was just the absolute change in position? Energy follows the same kind of rules here. The dx in the work function is a displacement. So it is path independent. Now that doesn't mean that there can't be things on the path that will change something's energy. Friction is a good example. Friction is a non-conservative force. So a longer path means you're going to be exposed to more friction, which means it will take more energy out of the system. So taking a convoluted path, if there's a non-conservative force, does make a difference. So when we talk about this absolute change in position is the only thing that matters, that only works if you're dealing with conservative forces. So this works because the electric force is a conservative force. It works for gravity because gravity is a conservative force. But non-conservative forces wouldn't obey those same principles. Still okay? Because there's something important I want to state now that I need to add to this. All this work was to get an expression for the change in potential between these two places, between 1 and 2. Now, is it obvious to you that if I had placed a positively charged particle here, it would be pushed away from Q, right? And it would go wherever. Consider that we could figure out more information, some interesting stuff in my opinion, something that's going to have a worthwhile end. What if I wanted to figure out the absolute change in potential? Meaning, what is the absolute potential at 1 relative to a place where the particle experiences no influence from the central charge? We did this for gravity, if you'll recall. We talked about trying to figure out what the absolute gravitational potential energy was. We did that in mechanics, which means comparing this location in space with a location very far away. If we look at our results, I'm just going to get all this out of the screen so I can look at just what I want. We said that the change in potential from V1 to V2 was Q over, let me use a little q, Q over 4 pi epsilon naught R2 minus Q over 4 pi epsilon naught R1. Right? What if we let R2 go to infinity? Right? Infinitely far away means no influence from the central particle. Right? I would imagine that voltage at that level would be 0 because this component would be 0. Does that make sense? So I'd have 0 minus V1 equals 0 minus Q over 4 pi epsilon naught R1. We're all okay so far? So that just means that the voltage, the absolute voltage, the absolute electric potential, not the change in electric potential, but the absolute electric potential at R1 is equal to Q over 4 pi epsilon naught R1. This is the electric potential around a point charge. It's one of those foundational things you need to know. For a number of reasons, but the most important one is the potential for a point charge tells you a lot. Like, consider this. How fast would a particle be going if I released it from here and let it spirit off by itself? Well, I know that the absolute potential energy would have to be the value of the charge times the absolute potential. So if I place charge Q here, the potential energy that particle had would be Q times Q over 4 pi epsilon naught R1. That's how much potential energy it would have there. If I let it go, isn't it true that all that energy will become kinetic energy? Well, if it all becomes kinetic energy, pretty sure I can figure out how fast it's going when it's far, far away. Now think of the reverse of this. a proton here. If I want to figure out how much energy it would take to cause a fusion event in an atom, then all I need to know is how close do I have to get the two protons together for the strong nuclear force to bind them together. Right, this is the amount of energy to cause nuclear fusion. It's right here. It's got to be based on Q times Q over 4 pi epsilon naught R, where R is the minimum distance necessary for the strong nuclear force to bind the nucleus together. If I know what that value for K is, I know how much kinetic energy I have to have. And since kinetic energy is proportional to temperature, I know how hot I need to get something. This is how you predict how hot stars are. Right? This is what stars are doing. And because stars are doing this, we can predict their temperature at the center. We know how hot the protons have to be for the proton-proton cycle to take place. We can't measure the temperature inside a star, but we know all of these other things. So this is how you know how hot the center of a star is, because we know what the proton-proton cycle is like. We actually worked it in reverse. It'd be like something like that, right? And then a topographical map suggesting that either this part right here is very high or very low. It's hard to know because I didn't put any kind of elevation data on it. Well, a topographical map can give you an impression of what the energy would be like if you placed an object somewhere. So if I have that rock and I place the rock, if I tell you that this is, 1,000 feet, this is 2,000 feet, this is 3,000 feet, and this is 4,000 feet, suddenly this map starts to make more sense, doesn't it? Can you tell from this map where the slope is steeper, like where it might be more difficult to climb if you're going mountain climbing or rock climbing? And can you tell where it's going to be, shallower? Obviously where the lines are more spread out, the gradient is going to be shallower, and where the lines are closer together, the gradient's going to be steeper, right? You guys get that idea? And you also should understand then that as you move from the low areas to the high areas, it's going to take work and it's going to give an object potential energy, gravitational potential energy. Well, when we find information about the potential, we're doing the same thing. A region of space can have potentials. These lines would be considered an equipotential line, because the line represents a certain potential. Everything on that line is at the same potential. So in this region of space, a positive particle will have more energy in some places than in others. In fact, if I just label A, B, C, D, E, where would a positive particle have more energy? A, B, C, D, or E? It's hard to tell between C and D, isn't it? I think it's likely C because it looks like C is closer to the next equipotential line, higher up. Wouldn't you agree? You guys see what I'm trying to indicate here, right? Now, a negative particle is going to behave in the opposite way. A negative particle will have more energy towards the areas with lower potential, because a negative particle behaves oppositely a positive particle. But the map tells you the same kind of thing that elevation tells you if you consider an elevation map. And so when we think about potentials, they're not much different than thinking about electric fields. But one of the major differences is, in the case of dealing with the potential, is that the potential builds a map of the space. An electric field didn't really. Electric field told you what the force would be like in a region of space. But this tells you what the energy is like in a region of space. They're similar. We know there's a relationship between the field and the energy. And we've talked about that relationship at length for the last couple of days. But when we build the idea of voltage, or we get an expression for voltage, we're kind of building out where the energy will be greater versus where the energy will be less. So one thing we knew, or we talked about already, was that if you had a region of space with a uniform electric field, then finding the electric potential wasn't that tough to do because it was easy math. But consider this. If this is my electric field lines, and I say that they're nice and evenly spaced, does it make sense that the change in potential if I move this distance d would have to be the same as a change in potential if I move the same distance d here? Does that make sense? Because we've talked about change in potential already for a uniform electric field. We know that the change in potential energy has to be QED. And if I'm talking about, bless you, the change in potential, then it's just E times D. And that would suggest for this drawing that there would be equipotentials that are evenly spaced, because every change in D is the same change in potential. Does that make sense? Can you guys see that okay? So if I was a positive particle, this could be, say, if I made up just some numbers here, positive particles gain energy going this way. So this amount of potential and this amount of potential and this amount of potential would be continually increasing as I went from one area to the next, because it would take work to get this positive particle down to the bottom of the screen. All okay so far? Now, these equipotentials are evenly spaced, and that's because our electric field is uniform here.